second example. Let's pick up another example. As you find on the screen, here you are going to find a tree in which you have, this is a BST. Check out if this is a BST or not. Yes, all the elements on the left hand side, that is 1, 3, 6, 4, 7 are lesser than 8. And all the elements on the right hand side, 10, 14, 3 are greater than 8. So therefore, this is an example. Now, the algorithms are all there on the screen. Now, according to this algorithms, let's try to trace down first the in-order traversal. Okay, so let me take time to first do the in-order traversal of this tree. Yes. How do you do the in-order traversal of this tree? In order, let's check out. This is the first one. We are doing the first one, that is in order. What is in order? In order says traverse through the left subtree. That means go to the left subtree until you find a node which has no more lefts. So therefore start at 8. This is how you do. You start at 8. Is 8 a parent? Yes. Is it having a left child? Yes. So go towards its left. Is 3 a parent? Yes. Before seeing a parent, you always got to see in order. Check out. Before seeing a parent, root is parent. Before seeing a parent, you always need to see its left child. So before visiting 3, you got to go and visit its left child. So therefore, now 1, is 1 a parent? No, 1 is a leaf node. Because 1 is a leaf node, write its left child, that is 1. Then go back and see its parent. Because after writing a left child, you have to see root. Root is nothing but its parent. Okay. So therefore, go and see its root. Okay, it's 10. You first have 1. Then go back and write its parent, that is 3. Okay. Then after seeing the parent, you have to see the right child. The right child is 6. But the right child seems to be a parent again. The right child seems to be a parent again. So therefore, because the right child seems to be a parent again, what do you do? Before seeing a parent, go and see its left child. So what is 6's left child? 6's left child is 4. And after writing a parent, go and see after writing a left child or visiting a left child, go and see its parent, that is 6. Then 7. So we are done with the left hand side of the tree. After done with the left hand side of the tree, it's time for us to update with the parent of the tree. The root of the tree is 8. Okay. Now then go to the right hand side of the tree. 8 has a 10. 10 is its right child. Now is it a parent? Yes. Is it having a left child? No. So therefore write down 10. Then write down the right child, that is 14, but 14 is a parent. Remember, always before writing a parent in an in-order traversal, got to write its left child. So the left child is 13 and the parent is 14. This is the meaning of traverse through the left subtree, visit the root and traverse through the right subtree. Okay, this is, if you can check out 1, 3, 4, 6, 7, 8, 10, 13, 14 is exactly the ascending order of the input. Is exactly the ascending order of the input. So that is the conclusion drawn from the given in-order traversal. Now let's do the pre-order traversal. The first and the foremost thing that anybody can write blindly by just seeing a tree in the pre-order traversal is first put the root of your tree, because pre-order says first the parent, only then its children. Okay, and that too left child followed by right child. So therefore is 8 a parent? Is 8 a parent? Yes. So therefore write 8. After that, go to its left child. Is 3 a parent? Yes. Then write 3. Is its left child 1 a parent? No. So therefore write its left child, then get back to the right child. That's how the story continues. So therefore 8 is a parent, then followed by 3, then 1, then its right child 6, then its left child, and then its right child. You can understand clearly when I write 6, 4, 7. First the parent, then its left child, then the right child. Now get back to the right child. The right child is 10. Okay, is 10 a parent? Yes. So write down your parent first. That is 10. Okay, then see its left child, but 10 has no left child. So therefore go and see its right child, which is 14. But 14 a parent? Yes. Write the parent and then come back and see its left child, which is 13. But 14 has no right child, so stop the business. The answer is 8, 3, 1, 6, 4, 7, 10, 14, and 13. And this is the pre-order traversal of this given tree. Now, when we got to extend the definitions, we now got to talk about pre-order traversal. So what is we have to talk about post-order traversal. The last of the traversals of DFS. The last of the traversals of DFS. The last of the traversals of DFS, which is post-order. So how do you do the post-order traversal of this BST? Yes, post order starts with the left child, then the pair, then the right child, and then the parent. So the last thing, the first thing that everybody can remember is write your root of the tree to the end. This is the last one that you will get here. Whatever comes before comes here. So first all the LST elements comes, then all the RST elements comes. So let's try to fill in the blanks. It starts with 8, but if 8 is a parent, go and see its left child. That is 3. Is 3 a parent? Yes, go and see its left child. That is 1. 1 is not a parent, so write down its left child. Then go and see the right child. The right child of 3 is 6, but 6 is a parent. Before writing the parent, write its left child 4, write its right child 7, then write the parent 6. So we are done with 1 and 6. 1 and 6 are the childs of 3. So therefore, go and write the parent 3. So this is the blank that fills in when you talk about the left subtree. And then if I now talk about the right subtree, the right subtree contains 10. Is 10 a parent? Yes. So therefore, go and see its left child first, but 10 has no left child. So go and see its right child, but the right child 14 is a parent again. So therefore, before writing 14, go and see its left child. The left child is 13. The left child is 13. No right child, so therefore write its parent 14. So the answer is 1, 4, 7, 6, 3, 13, 14 and 8. And this is how we perform the post-order traversal of a given BST. When we got to write about, this is the function which we have already seen. This is the function for post-order. This is the function for in-order and this is the function for pre-order. But before all this, it's time for us to exactly check out how do you write a logic for a BST traversal. So when we got to write a logic for a traversal of a binary search tree, let us first try to create a BST with these elements. Okay, let me just try to create a BST with these elements and fill in the blanks for the next traversal. My elements are 9, 16, 4, 7, 1, 10, 3. Why am I giving these elements? Is when I run my code, I have to understand at least what is the answer that I'm going to get right. So therefore, let me just, okay, control that, sorry. Let me just create a BST with these elements. 9, 6, 4, 7, 1, 10, 3. 9, 6, 4, 7, 1, 10, 3. Not that my program only runs for these elements, it's for quick reference, okay, because I have an answer available. So whatever comes in the first is your root. So 6 is lesser, 4 is still lesser, 7, 7. Where do you put 7? This is the same logic. How do you insert element into a BST? 7 is lesser, so greater than 6, so therefore 7 here. Okay, 1 is still lesser, so 1 becomes a child here. 10 and 3. 3 is lesser than 4, so again 3. Array. Okay. So now, this is your tree. Got to perform your in-order and pre-order traversals, then you will be able to get the answer. So take a minute's time. Let's take a minute's time, look at the tree and try to perform the in-order and pre-order traversals. Meanwhile, we'll see how does the logic goes. So yes, your BST has a left child and a right child, 2 pointers that hold its left subtree and right subtree, a data where it stores the value. The root is null, in-order, pre-order, and post-order. You'll create a BST and display using these 3 techniques. A main function which calls create BST followed by in-order, pre-order, and post-order. Create BST puts the elements on the left side of the tree if the values are lesser, puts the elements on the right side of the tree if the values are greater or equal. Whenever you find a position of a leaf node, then you start adding your elements. This is the in-order traversal. Any technique continues until the root is not null. Root is that particular place where you reach a leaf node. When you beyond the leaf node, there's nothing for a tree. So therefore, we stop when we reach a leaf node. In order for left, then print the root's data, then in order of root of right. This is how we work out to perform the traversals of a binary search tree. The function is already discussed. Just check once again. We'll try to trace down also if possible. Let's first run the code and see. Okay, so let's first run the code. A detailed discussion about all these techniques will also be given when we discuss more about theory. Okay, as a part of lab program, it's extremely important for us to quickly understand what the logic basically talks about. So the logic here basically talks about, that recursive technique which has a base case as root not equal to null, repeats until the root is not equal to null. So when I run this code, let us take a simple binary search tree with 10 as root, or this example that we have already taken. Okay, well, let's take this example that we have already taken. 8, 3, 10, 1, 6, 14. Okay, let me do it. Let's run the code. Let's give the elements. If you want to insert, you have to continuously press 1, 8, 3. Okay. 8, 3, 10. Inputs are 8, 3, 10, 1, 6, 14, 1, 6. 8, 3, 10, 6, 15. Okay, enter your choice 1, 15. 8, 3, 10, 6, 15. This is what my input is. 8, 3, 10, 6, 15. So when you give your input as 8, 3, 10, 6, 15, let's see how the 8, 3, 10, 6, 15. So this is your tree. What is its in order? In order is left child. So it is 3, 6, 8. In order is simple. Just put all of them in ascending order. You'll get in order because it is BST. What is pre-order? Pre-order is first the root 8, then the root again 8, then 3, then 6, then 10, then 15. Write all the parents the way you encounter them. Then the post order, first the left child. You don't have a left child, then the right child, then the parent. Go back to its left child, no left child. So therefore right child, parent 8. So this is my answer. Let us check out if we get the right answer or not when we run the code. Okay, I'm pressing 2. 2 is for in order traversal. We got 3, 6, 8, 10, 15. 3, 6, 8, 10, 15. Let's check out if the in order is 3, 6, 8, 10, 15. Yes, for this example, we got 3, 6, 8, 10, 15 only. Now let's give 3. 3 stands for pre-order. So the pre-order traversal is 8, 3, 6, 10, 15. The pre-order traversal is 8, 3, 6, 10, 15. Oh, correct. Next one, let's press 4. That is for post-order traversal. The post-order is 6, 3, 15, 10, 8. The post-order is 6, 3, 15, 10, 8. Yes. So therefore, for any random given tree, I got my answer correct. And this is the output of my code. Okay, this is the output of your code. If you want to understand how is recursion going or how is recursion executing, it stops when it reaches the base case. What is the base case? If root is equal to null. If you want to simply understand, let us trace it down for pre-order. Pre-order says what? Let us have the address first. This is root. Let us have the addresses as 100. 200, 300, 400 and 500. It's only for our reference. Let's start at 100. Is 100 having pre-order? I'm doing pre-order. Pre-order says first print the root, then print the left child, then print the right child. So therefore, printf percentile D, root arrow data. Root is 100, 100 arrow data is 8. So it prints 8. Then calls pre-order of root arrow left. Root arrow left is nothing but 200. So it now goes and calls pre-order of 200. But when I have pre-order of 200, pre-order of 200 first prints the value at 200. So therefore it prints 3 and then calls pre-order of root arrow left. Is 300 having any element towards its left? No. So therefore the answer is null. Pre-order of null. Pre-order of null. So when I take this definition, pre-order of null means if root is equal to null, return. I'm stopping the process here, ending the call here when I have null. So this is how you close your business and this is how we exit from the recursive calls. If you want to understand much more clearly, then once trace down the logic. Okay, once trace down the logic, that gives you a lot of clarity. At this point of time, this is an example from which you can understand how is traversal of trees possible. Yes, we can make an iterative version of it as well. Yes, we can make an iterative version. Iterative way of DFS traversals as well, but that is little typical. The code requires a lot of lines and it employs a data structure called stack. We need to take the help of stack because backtracking does not happen by a returning root. Backtracking must happen here by storing the nodes in stack. So yes, the recursive traversal are easy, simple, easy to remember, and a very important exam point of view question. So please kindly concentrate and prepare. See you with the next video. Thank you.